In this section, we're going to look at subspaces. A subset W of a vector space V is a subspace of V if W is non-empty and a vector space itself with the same operations as V. For example, the set W given by the set of all pairs x0, where x is real, is a subspace of V equals to R2. Okay, if we look at the xy plane, then all the points in this plane forms the vector space R2. But W is the subset of R2 consisting of those points along the x-axis. Okay, so x0, the y-coordinate is 0, so it's just going to be all those points along here on this x-axis. Okay, so the claim is that that line, the x-axis, is a subspace of the bigger space R2. Okay, now to show that W is a subspace of R2, we have to show that W has all those 10 vector space properties. Okay, what I mean is that normally one would have to show all 10 of those vector space properties. Fortunately, we don't have to show all of those properties, we just have to show a few of those. So we have to show 2 closure properties, and we have to show that W is non-empty. And to show that W is non-empty, we can show that it contains the 0 vector. Okay, so let me write the subspace properties. Subspace properties. Okay, there's only 3 of them. The first one, the 0 vector lies in W. The sum of 2 vectors from W lies in W. Okay, this is called closure under addition. And the third property is that C times U lies in W. Where C is a scalar and U is a vector from W. Okay, this is called closure under scalar multiplication. Scalar multiplication. Okay, let's do an example. Let's say W is the set of all x0, where x is in R. and the big space V is R2. Okay, let x be 0. Then x0 is 0, 0. And 0 lies in R. So the 0 vector, which is 0, 0, lies in W. Okay, now for the second property, let U be x0 and let V be y0. Where x and y are real. Okay, I just picked two arbitrary vectors, u and v, from W. Now I want to add u and v. Okay, so now I get x plus y, 0. And that lies in W, since x plus y lies in R. Okay, x plus y lies in R, and so the first component is real, and the second component is 0. But that's just what W is. It's all of those pairs x0, where the first component is real. Okay, so this right here lies in W. Now for the third property, let C be a scalar and let U be some element x0 in W. Then C times U equals C times x0 which is Cx C0, but C times 0 is 0. Okay, and this does lie in W because Cx lies in R. Okay, since C and X are both real numbers, when I multiply them, I get a real number. And so this first component is real, the second component is 0, and so this vector lies in W. Okay, so we do have closure under scalar multiplication. So W is a subspace of R2.